Hi, my name is Angela Gaetano. I go to school at Belmont University in Nashville, Tennessee. And this summer I did research with Dr. Scott Linder on the impact of censoring on the estimator of the slope parameter in a simple regression model. So the purpose of this is to, in a way, find unknown sampling distributions that are imposed when you censor data, when doing basic statistics like simple regression. So what is censoring? Censoring, in many applications, data used for inference are subject to censoring. This particular type of censoring we looked at is in the case that a researcher would decide ahead of time that even though they have a full sample of, say, 20 items, this case here, we can talk about light bulbs. So 20 light bulbs, but they're deciding ahead of time to only wait until the 10th light bulb dies out. So this is called type 2 right censoring, and this picture right here shows that a little bit. This is the full sample plotted, and this is the censored sample. And what this does is it imposes an ambiguity onto this particular parameter, beta hat, and it is the estimator of the parameter beta. This is the statistics for that parameter. And what happens is the slope of the fitted line to these points will change every time you run the experiment, but when you censor, it will change on average more than with the full sample case. So what we're looking at is how this change in the slope varies, and that's why we're going to take a look at variance of beta hat. So here's some basic properties of beta hat. Expected value of beta hat is beta, so it is an unbiased estimator with or without censoring. And what that means is that on average, your estimate for the slope will be the true value of the population slope. Also, here's the variance beta hat issue again. And what we're looking at, it's a little easier to see up here. This piece of the variance of beta hat equation is the part that's mathematically intractable. It's based on your actual data, whereas these are just the theoretical parameters. So what we're going to do is we simulated this value over and over again. So this is the plot of those simulated expected values of 1 over SXX, which, by the way, is just a measure of spread across the x's in your data. So what we wanted to do was fit a surface to the simulated data by way of a regression model. So we found a regression equation that would fit these points pretty well, and we were going to plug it in for this otherwise unknown piece of the formula. So here's the output of that. Here's the output of the variance of beta hat when we plug in the regression equation. And here's just the variance of beta hat values based on the simulated expected values. We put a relative error column here just to show that the error increases in general as you censor less. So this provides estimates for expected value of 1 over SXX, but they are poor when p is close to n. So they're good when censoring is more severe, but it's not going to be able to be used incredibly well at this point. We might have to find a better regression function to estimate this. More interestingly, we have the power of testing for independence. So we're testing that beta equals 0 against beta does not equal 0. And the power is simply the ability to detect a lie when you're doing hypothesis testing. So we want to, if we want to prove that this is true, that beta does not equal to 0, which is important, we want to be able to do that with high probability, with high power. So we ran a simulation that would allow a researcher to then pick out an N and P, so pick out the level of censoring associated with their particular sample size, and find how much they would have to censor in order to get a desired power. So say the researcher wanted to have a power of 60%, and they're going to state ahead of time that the true beta is 0.6. So then they can just look here and say, well, if I have 20 in the sample size, I have to wait until the 17th light bulb dies. Whereas if I had 30 in the sample size, I only have to wait till the 22nd dies. So that's up to the researcher. You know, there's cost benefit there. Buy more, but have a shorter experiment time. There's definitely future work involved in this. We could find better ways to visualize this. We could make the regression function, make a regression function that's, you know, dependent on different variables. Like instead of N and P, perhaps look at rho and the ratio of sigma y to sigma x. So yeah, and this would give a tool for researchers to be able to censor their data, which is very beneficial. And that's it. Thanks for listening.